present video we will discuss the gate previous questions of queuing theory. We know the important formulas of single server and multi-server queuing model. Let's see the first question. For a single server with Poisson arrival and exponential service time, the arrival rate is 12 per hour. Which one of the following service rates will provide a steady state finite queue length? So we know the procedure of solve the queuing problems. First step is we have to identify the queuing model. Next we have to identify the lambda and mu values from the given data. Then write the required formulas and substitute lambda and mu values. So let's see the solution. Here it is given the queuing model is the single server queuing model and arrival rate is given, that is 12 per hour. So which means lambda equal to the 12 per hour. So then we have to identify the service rate, mu value we have to identify, and moreover, so which it will be provide a steady state finite queue length. Okay, so let's see the solution. So let imagine a ticket counter. Let consider lambda is the arrival rate, which is the number of customers coming per hour, and service rate mu equal to the number of customers served per hour. So in this problem, customers arrive at 12 per hour, so lambda value is the 12. So let's see the first case. If the mu is less than the lambda, which means service is slower than the arrival. So let's consider mu value is the 10 customers per hour, which is less than the lambda, but lambda value is the 12 customers per hour, which means 12 customers are coming per every hour. But here service is the only 10 customers are served every hour, which means for every hour 2 customers are left behind. In this regard, queue is keeps getting longer and longer, which result in a not a steady state. So it is the unstable system. So here option A is 6 per hour, which is the less than the lambda, and similarly option B 10 per hour, which is also less than the lambda. So if mu is less than the lambda mean, so it is the not a steady state. So let's see the case 2. Case 2 is mu equal to the lambda. So where the service is equal to the arrival. So in the data it is given the lambda equal to the 12. Then let's consider mu also equal to the 12, which means 12 customers are coming every hour and 12 customers are served every hour. In this regard, server is always busy all the time. So even a small delay can cause the queue is to grow. So this is also not a stable system. So if the mu is less than the lambda and mu equal to the lambda, system is a not a stable system. So let's see the third case. So mu is greater than the lambda, which means service is faster than arrival. So let's consider mu is greater than, which is the 24 customers per hour. So here 12 customers are coming every hour and 24 customers can be served every hour. In this regard, server can clear customers faster than they arrive. So queue remains short and controlled. So this system is the stable system with finite queue length. So for a steady state and finite queue length, mu is always greater than the lambda. So in the given options, only option D is greater than the lambda. So option D is the correct answer. Next question is, in a single channel queuing model, The customer arrival rate is 12 per hour and the surveying rate is 24 per hour. The expected time that a customer is in queue is dash minutes. So let's see the solution. Here given model is the single server queuing model and in the data it is given the arrival rate. So arrival rate 12 per hour which is belongs to the lambda. So lambda value is 12 and the surveying rate is 24 per hour. So which is the mu. So mu equal to the 24. So then you have to determine the expected time that a customer is in queue. So in the minutes, we have to determine it is in the minutes. So we know the formula average waiting time in queue. WQ equal to the WS minus 1 by mu which is equal to the 1 by lambda into LQ. So we know the LQ formula, that is the average number of customers in the queue. LQ equal to the LS minus lambda by mu which is equal to the lambda by mu into lambda divided by mu minus lambda. So here we know the lambda value as well as the mu value. Then substitute LQ equal to the 12 by 24 into 12 divided by 24 minus 12 which is equal to the 12 and 12 get cancelled. Then LQ equal to the 1 by 2. So we know the LQ value which is equal to the 1 by 2. Then WQ equal to the 1 by lambda which is equal to the 1 by 12. So 1 by 12 into 1 by 2. Then WQ equal to the 1 by 12 into 1 by 2 which is equal to the 1 by 24 hour. But we need the answer in the minutes. Then I have to convert hour into the minute which is equal to the WQ equal to the 1 by 24 into 60 which is equal to the 2.5 minute. So answer is the 2.5 minute. Next question is in the notation A, B, C, D, E, F for summarizing the characteristics of a queuing situation, the letters B and D stands respectively for. So we know the Kenley queuing notations. So A, B, C, D, E, F. So where A is the arrival distribution, B is service time distribution, and C is number of servers, D is queue discipline, E is maximum number allowed in the system, F is size of the calling population. So here B and D. B is the service time distribution and D is the queue discipline. So B and D. Service time distribution and queue discipline. So option A is the correct answer. Next question is the jobs arrive at a facility for service in a random manner. The probability distribution of number of arrivals of jobs in a fixed time interval is option A normal, option B Poisson, option C Erlang, option D beta. So we know that when the probability distribution of the arrival is the Poisson. So option B is the correct answer. And next question is customers arrive at a ticket counter at a rate of 50 per hour and tickets are issued in the order of their arrival. The average time taken for issuing a ticket is 1 minute. Assuming that customer arrival form a Poisson process and service time are exponentially distributed, the average waiting time in queue in minute is option A 3, option B 4, option C 5 and option D is 6. So let's see the solution. So here it is the single server queuing model and arrival rate is given. Arrive at a ticket counter rate of 50 per hour. So lambda is 50 per hour. And also given the surveying time 1 minute. So here it is given the average time taken for issuing a ticket is 1 minute. So surveying time is the 1 minute which is equal to the 1 by mu. Then mu equal to the 1 customer per minute, but lambda is given in the hour. So you have to convert then 60 customers per hour. So we know the lambda and mu values. Then we have to determine the average waiting time in queue in minutes. We have to determine in minutes. So we know the formula average waiting time in the queue. So and first we have to determine the LQ. So length of the queue, which is equal to the lambda by mu into lambda divided by mu minus lambda. So then LQ equal to the, so lambda is the 50 and mu is the 60. So 50 by 60 into 50 divided by 60 minus 50. So it is the 10 and 0 cancel, it will be 5. So here also 0 get cancelled. Then so 25 by 6 or 250 by 60. So we know the LQ value, then substitute WQ equal to the 1 by lambda, 1 by 50 into 250 divided by 60. So WQ equal to the 1 by 50 into 250 divided by 60. So here 0 get cancelled and 5. So WQ is the 5 by 60 hour, but we need the in the minutes. So 5 by 60 into 60 minute. Then 60 get cancelled. Then answer is the 5 minutes. So option C is the correct answer. So next question is, cars arrive at a service station according to Poisson's distribution with a mean rate of 5 per hour. The service time per car is exponential with a mean of 10 minutes. At a steady state, the average waiting time in the queue is. So first I have to identify the lambda and mu values. So arrival rate, it is given the 5 per hour. So 5 cars per hour. So lambda value is the 5 per hour. And service time is given, which is the 1 by mu. It is the 10 minutes. So then the serving time is the 10 minutes, which is equal to the 1 by mu. Then mu equal to the, so 1 divided by 10. So 1 car divided by 10 minutes. So for the hour point of view, so 6 and 6, 60 minutes is equal to the hour, and 6, 1 into 6, 6. So mu equal to the 6 cars per hour. So we know the lambda value and mu value. So I have to determine the average waiting time in the queue. So we know WQ equal to the 1 by lambda into LQ, and LQ equal to the lambda by mu into lambda divided by mu minus lambda. Substitute lambda and mu values. Then LQ equal to the 5 by 6 into 5 divided by 6 minus 5. It is the 1 and 5. So 25 by 6. Then substitute LQ value in the WQ equation. WQ equal to the 1 by 5 into 25 by 6, which is equal to the 5 by 6 hour. But here is required in the minutes, all the options. So 5 by 6 hour, which is equal to the 5 by 6 into 60 minute. Then it will become the 50 minutes. So option D is the correct answer. Let's see the next question. In an MM1 queuing system, the number of arrivals in an interval of length t is a Poisson random variable where probability of there being n arrivals in an interval of length t is e to the power minus lambda t into lambda t whole to the power of n divided by n factorial. The probability density function f of t of the inter-arrival time is given by. Okay, so let's see the solution. So for a MM1Q is the arrivals follow a Poisson process with a rate lambda, and the inter-arrival are exponentially distributed. Then probability density function PDF of an exponential distribution with rate lambda is the f of t equal to the lambda into e to the power minus lambda t, where t is greater than or equal to the 0. So therefore f of t, probability density function f of t equal to the lambda into e to the power minus lambda t. So option C is the correct answer. So let's see the Next question. The number of customers arriving at a railway reservation counter is Poisson distributed with an arrival rate of 8 customers per hour. So here it is the arrival rate of 8 customers per hour. So which is nothing but lambda, arrival rate is given. So lambda value equal to the 8 customers per hour. So 8 per hour lambda value. The reservation clerk at this counter takes 6 minutes per customer on average with an exponentially distributed service time. So here it is given the service time 6 minutes per customer, which is equal to the 1 by mu, which is equal to the 6 minute per customer. Then mu equal to the 1 customer divided by 6 minute, which is equal to the, so here you have to into 10, and here it is equal to the into 10. Then 60 minute will become the hour. So then mu equal to the 10 customers per hour. We know the lambda value and mu value. So then you have to determine the average number of customers in the queue, which is nothing but LQ. Average number of customers in the queue, LQ equal to the lambda by mu into lambda divided by mu minus lambda. So we know the lambda value and mu value. Substitute, we will get the LQ equal to the 3.2. So option B is the correct answer. Let's see the next question. Consider a single server queuing model with Poisson arrivals lambda equal to the 4 per hour and exponential service mu equal to the 4 per hour. The number in the system is restricted to a maximum of 10. The probability that a person who comes in leaves without joining the queue is. So let's see the solution here. So lambda and mu, arrival rate and service rate is given. Both are the 4 customers per hour. And here maximum number allowed in the system is 10. And this is belongs to the model of the, so MM110. So which means, so arrival is the Poisson and surveying is the exponential, and single server and queue length maximum restricted to the 10. So single server with fine capacity of the 10. The probability that a person who comes in leaves without joining the queue. So how to determine? So probability who is not joining the queue. So first we have to determine the traffic intensity, rho equal to the lambda by mu, which is equal to the 1. So when rho equal to the 1, then steady state probabilities are equal to the probability that belongs to Pn. So which is equal to the 1 divided by capital N plus 1. So where the small n, which is equal to the, so 0, 1, 2, 3 up to the capital N. And here capital N, which is belong to the 10, then probability that Pn equal to the 1 by 11. So a customer leaves without joining the queue only when the system is full. So when there is already 10 customers in the queue in the system, then P of leave equal to the P of 10. Then P of 10 equal to the 1 by 11. So option A is the correct answer. Let's see the next question. The cost of providing service in a queuing system increases with option A, increased mean time in the queue, option B, increased arrival rate, option C, decreased mean time in the queue, option D, decreased arrival rate. So in queuing theory, reducing the average waiting time in the queue generally requires more servers, faster service rates, better service facilities. So to reduce the average waiting time in the queue is we have to require more number of service and faster service rate and better service facilities. These improvements increase the service cost. So therefore, lower mean waiting time, which is belongs to higher service cost. Higher mean waiting time belongs to the lower service cost. So this reflects the trade-off between the customer's waiting cost and the service facility cost. Hence, the cost of providing service increases when the mean time in the queue decreases. So in this regard, so option C, the cost of providing service in a queue system increases with decreased mean time in the queue. Option C is the correct answer. Let's see the next question. Jobs arrive at a facility at an average rate of 5 in an 8-hour shift. So here it is given the arrival rate is given. So that arrival rate, jobs arrive at facility at an average rate of 5 in an 8-hour shift. So this is belongs to lambda equal to the 5 jobs per 8 hour. The arrival of the jobs follows Poisson distribution. Average service time of a job on the facility is 40 minutes. So service time. So service time of a job on the facility is 40 minutes, which belongs to the service time in 1 by lambda. So 1 by lambda equal to the 40 minutes per job. Then you have to convert into the hours, mean 40 divided by 60, which is equal to the mu equal to the 60 divided by 40 jobs per hour, which is equal to the 3 jobs per 2 hours. Then we have to find the ideal time at the facility per shift will be. So I have to determine the ideal time. So we know the probability that server is ideal, P naught equal to the 1 minus lambda by mu. So here we know the lambda value and mu value, substitute, we will get the P naught server is ideal equal to the 7 by 12 hour. But we need the in the per shift is required. So then ideal time at the facility per shift will be 7 by 12 into 8, which is equal to the 14 by 3. So option B is the correct answer. Then next problem. At a workstation, 5 jobs arrive every minute. The mean time spent on each job in the workstation is 1 by 8 minutes. The mean steady state number of jobs in the system is dash. So here it is given the arrival rate. 5 jobs arrive at every minute, which belongs to the lambda equal to the 5 jobs per minute. And mean time spent on each job in the workstation is 1 divided by 8. So this is belongs to the mean time. So service time. Mean time spent on each job in the workstation is 1 by 8 minute, which is equal to the 1 by mu. 1 by mu equal to the 1 by 8. Then mu equal to the 8 jobs per minute. We know the lambda value and mu value. Then we have to determine the mean steady state number of jobs in the system. So LS, we know the average number of customers in the system. LS equal to the lambda divided by mu minus lambda. Then it is the 1.67. So answer is the 1.67. Let's see the next question. A maintenance service facility has Poisson arrival rates, negative exponential service time, and operates on first come first served queue discipline. Breakdowns occurs on an average of 3 per day with a range of 0 to 8. The maintenance crew can service an average of 6 missions per day with a range of 0 to 7. The mean waiting time for an item to be served would be. So option A, 1 by 6th day. 1 by third day, 1 day and third day. Okay, so let's see the solution. So here a maintenance service facility follows MM1 queuing model. So because here arrival is the Poisson distribution and service is the exponential distribution, and so first come first service discipline. So and also given the breakdown occurs on an average of 3 per day. So it is belongs to the arrival rate. Breakdowns occurs on average 3 per day. So let's consider lambda equal to the 3 missions per day, and maintenance crew can service an average of 6 missions per day. So and service rate, that is the mu equal to the 6 missions per day. So lambda we know and the mu also we know. Then we have to determine the mean waiting time for an item to be serviced would be. So I have to determine the mean waiting time. So mean waiting time in the queue is WQ equal to the 1 by lambda. So 1 by lambda into LQ. So we know LQ equal to the lambda by mu into lambda divided by mu minus lambda. Then LQ equal to the 1 by 2. Then WQ equal to the 1 by 3 into 1 by 2, which is equal to the 1 by 6th day. So option A is the correct answer. So have to convert. So option A is the correct answer. Let's see the next problem. Arrivals at a telephone booth are considered to be Poisson with an average time of 10 minutes between successive arrivals. So it is given the average time between arrivals, which is belongs to the 1 by lambda, which is equal to the 10 minutes. Then lambda equal to the 1 by 10, which means 1 customer per minute. The length of a phone call is distributed exponentially with mean 3 minutes. So it is given the mean service time 1 by mu equal to 3 minutes, then mu equal to the 1 by 3, which means 0.33 customers per minute. So we know lambda value and mu value. So then you have to determine the probability that an arrival does not have to wait before service is. So we know probability that server is ideal. So P naught equal to the 1 minus lambda by mu. So lambda equal to the 0.1 and mu equal to the 0.33. Then service is ideal, P naught equal to the 1 minus 0.1 divided by 0.333, which is belongs to the 0.7. So option C is the correct answer. So next problem. In a single server infinite population queuing model, arrivals follow a Poisson distribution with mean lambda equal to the 4 per hour. So in the data it is given the arrival rate lambda equal to the 4 customer per hour. Service times are exponential with an mean service time equal to 12 minutes. So here it is given the service time, which is belongs to the 1 by mu, which is equal to the 12 minutes. Then so have to convert, so minute into the hour, which is belongs to the 0.2 hour. Then mu equal to the 1 divided by 0.2, which is equal to the 5. So 5 customers per hour. So we know lambda and mu values. Then have to determine the expected length of the queue. So we know the formula LQ, length of the queue. So lambda by mu into lambda divided by mu minus lambda. Then so substitute lambda and mu values, then LQ equal to the 3.2. So option B is the correct answer. So let's see the next question. At a production machine, parts arrive according to a Poisson process at the rate of 0.35 parts per minute. So arrival rate lambda equal to the 0.35 parts per minute. Processing time for parts has exponential distribution with a mean of 2 minutes. So service time is given 1 by mu equal to the 2 minutes, then mu equal to the 1 by 2, which is equal to the 0.5. So 0.5 parts per minute. Then what is the probability that a random part arrival finds that there are already 8 parts in the system? So we have to determine the probability that there is n number of parts in the system, which is equal to the Pn, probability of the n number of parts in the system, Pn equal to the rho to the power n into P naught, where rho is the traffic density and P naught represents the probability that system is ideal, which is equal to the 1 minus rho. And also we know direct formula, also we know probability that there are n customers in the system, Pn equal to the, so lambda by mu whole to the power of n into 1 minus lambda by mu. So substitute. So here small n equal to the 8. So because here already given, already 8 parts in the system. So small n equal to the 8. Then P8, probability that 8 number of parts in the system, P8 equal to the, so lambda by mu 0.35 divided by 0.5 whole to the power of 8 into 1 minus 0.35 divided by 0.5. So this is belongs to the, so 7. So no, 0.7. 7 mean 3.5. So 0.7, 0.35, and here also, so 0.7. So P of 8 equal to the 0.7 whole to the power of 8 into 1 minus 0.7, which is equal to the 0.0173. So option C is the correct answer. Let's see the next problem. On the average, 100 customers arrive at a place each hour, and on the average the server can process 120 customers per hour. What is the proportion of time the server is ideal? So here it is given the arrival rate, so lambda 100 customers per hour and mu service rate 120 customers per hour. So then I have to determine the what is the proportion of time the server is ideal. So we know that probability that server is ideal, P naught equal to the 1 minus lambda by mu, which is equal to the 1 minus 100 by 120, which is equal to the, so 0 0 cancel, and LCM is the 12. 12 minus 10, so 2 by 12, which is equal to the 1 by 6. So P naught, probability that server is ideal, which is equal to the 1 by 6, 0.16667, which is equal to the 16.67 percentage. So therefore server is ideal approximately 16.67 percentage of the time. So this is the solution, and thank you.